Hi everyone, it's Tutoring here. Today we are going to be covering the grade 11 functions concept of radicals. When I say grade 11 functions, I mean according to the Ontario curriculum. If you are somewhere else in the world, this may be different depending on what course you're in, but generally speaking for Ontario students in Canada, this is a grade 11 concept. Okay, let's get into it. So let's start off by defining what a radical is. So, a radical is a square, cube, or higher root, such as root 4, square root of 4, which is equal to 2, or the cube root of 27, which is equal to 3. So I'm just going to write that out now, so you guys can refer to that for your notes if you want to. So a radical, I'm just going to repeat myself, is a square, cube, or higher root, such as 4, which we should know is equal to 2, and the cube root of 27, which is equal to 3. Okay, so there are three main parts of a radical expression or radical that we are going to break down now. So I'm just going to draw it out like this. I'm going to put just the variables a, b inside, and now we're going to label it. So this black symbol that we know as the square root symbol, but we can put like another number like here, say like 3 or 4, and then we can change the degree of the root we are taking. But this little kind of squiggly box, I guess you could say, is known as the radical sign. And then a, b, which are the variables that are underneath the radical sign. This is what is known as the radicand. Don't really like the way that word sounds, but the radicand or radicand or however you'd like to say it. And then this entire thing here, the radical sign and the radicand together is what is known as the radical expression. Now, for the purpose of grade 11 functions, and generally for the majority of high school math, unless you're taking something maybe like AP or IB, generally, as far as high school math goes in Ontario, when we talk about whatever is underneath the radical sign, whatever the radicand's value is, it must be greater than or equal to 1. So I'm just going to make a note of that. So if you see any negative numbers, you either did something wrong or multiplied incorrectly, or your teacher's trying to trick you or something, because that's not possible. You'll get an error. Later on, if you continue with math, you may discover that you can actually evaluate a negative number. You'll learn about like imaginary numbers and all that stuff. You'll be able to evaluate a negative number under the square root of a negative number and like whatever. But in this case, we're saying the radicand must be greater than or equal to 0. In this case. Alright, so we're almost done with the terminology. Then we can start to get into some problem solving. I think we need maybe 3 more definitions, and then we can get into doing some problems. Okay, I'm just going to move that up a bit. Okay. Oh, I guess it doesn't want to move up that much further. That's unfortunate. Alright, let's just move over. Sorry. Okay, so the next word we're going to, the next term we're going to learn is entire radical. I almost said the next word, but it's not a word, it's 2 words, the next term. So what an entire radical is it is a radical with a coefficient of 1. So an example of that would be something like root 7 or root 13. As long as there's no number in front of the radical, it pretty much can be really anything, as long as there's no number in front. Whereas our next term is what's known as a mixed radical. And a mixed radical is the opposite of an entire radical, and it is a radical with coefficient other than 1. So an example of that would be 2 times root 3, or 4 times root 5. You can even have a negative coefficient. You can have negative 2 root 10, and so on and so forth. You get the idea. Continuing. You can have lots of different mixed radicals. And then our last term that we have before we get into problem solving is the like radical. So what the like radical is like radicals are radicals that have the same radicand. So an example of like radicals would be something like 2 root 3 and 4 root 3. So what's inside underneath the radical sign, or what we just defined as the radicand, is the same. Both, it's 2 times root 3 and 4 times root 3, but root 3 is the radicand and it's the same, so they are like radicals. Pretty straightforward. Right? Okay. So let's move on to some examples. All right. So in our first example here, I want to simplify one of these radicals. So let's call this example A. And I want to simplify this radical. I have root 72. And I want to write this as a mixed radical. So what I want to do is I want to think if there is any number that I can write any way that I can write 72 as a product of a perfect square and another number. So I'm going to try to think of all of the multiples all the factors, of 72, and all the numbers I can multiply together to get 72. And if I think about it, I realize that 2 times 36 gives me 72. So 36 times 2 is 72. And what is so convenient about that is that 36 is a perfect square. And we know this because 6 times 6 is 36. So what we want to do is we want to replace this root 72 with root 36 times root 2, because if we were to multiply these radicals, we would get root 72. So we're not changing the value here. And now we can evaluate that root 36 is just equal to 6, like we did over here. We just proved that. Over here, this should be common knowledge by grade 11 that 6 times 6 is indeed 36. And then we're going to keep that multiplied by root 2 because we can't break down root 2 into anything else simpler. And then our answer is going to be the mixed radical of 6 root 2. I'm going to box it off, and that is the final answer for this example. All right. Just going to erase some of this. Let's do another example. All right, so say I have example B here, and I have the radical root 27, and I want to add it to root 36, square root 36. You can just say root because we can have different levels of roots. We can have cube root, we can have fourth root, we can have different degrees of roots, so I'm not going to just say root. In general, though, in this video, if I do say root, I'm probably referring to the square root of a number. So I'm taking the square root of 27 and the square root of 36, and I want to add them together, or at least I want to simplify this expression if I can't have two integers being added together. So what I want to do is I want to look at 27, and I want to see, is this a perfect square? And I'm like, I consider the factors of 27, and I determine that no, this is not a perfect square. So not a perfect square. So if it's not a perfect square, I want to think of if any of the factors of 27 are perfect squares. And if I think about that, I realize that 9 is a factor of 27, and 9 is a perfect square. It is 3 times 3 is equal to 9, so we can use that to simplify this first part of the expression. We can simplify this radical using that. So we can write root 27 as root 9 multiplied by root 3, and then if we simplify root 9, we get 3 times root 3. So now we finished the first part of simplifying this expression. Now we want to move on to the second part. So we're going to go back to root 36 and we're going to look at it and we're going to see, is this a perfect square? And actually our lives are very simple with this question because it is indeed a perfect square. So we can just evaluate it. We know that 36 is 6 times 6. So we can just write plus 6 over here, and then add plus 6 over here, and then we can box this off because this is our final answer. And we're done. I think I actually have enough room to put example C on the bottom here, so I'm going to go ahead and do that. Example C is pretty straightforward. We are just going to be adding 3 root 5 to 2 root 5. And because, as we mentioned before, whenever something has the same radicand, in this case the radicand is 5, they are like radicals, we can just add them together normally. So we are going to be adding, basically the front two terms are what we're going to be adding. The radicand is going to stay the same, so 3 plus 2 is 5, and then the radicand stays the same, so it's 5 root 5, and that is our answer. If you don't believe that this is true, you can go and check it out in your calculator. You can type in 3 root 5 plus 2 root 5 and see what number you get. It'll be some decimal number. And then you can go and type in 5 root 5 and you will get the same decimal number. All right, so moving on to our next example. Let's erase this. I was moving the slide up before, but I've kind of run out of space, so I'm just going to be erasing from now on. Okay, so now we have a longer expression that we're going to try to simplify. Longer expression using some radicals. So we have, this is example D, and in this example we have 3 root 108 plus 2 root 98 plus 4 root 147. Okay, so what we want to do is we want to kind of break this down into parts. I feel like it can be very intimidating to kind of look at this and you just try to go without kind of breaking it down step by step. So what I like to do is I like to tackle each radical at a time. So the first radical I'm going to tackle is 3 root 108. So 3 root 108, if I look at that, I want to look at the radicand inside. I'm not really concerned with the 3 as much. I will be later, but not right now. So I want to see what numbers I can multiply to give me 108, and if one of these numbers is indeed a perfect square. So I'm going to be considering the factors of 108, and then after I consider that, I realize that 36 has been showing up a lot in this video, I'm sorry. 36 is a perfect square and it is a factor of 108. So 36 times 3 gives you 108. So I'm going to write 3 times root 36 times root 3 is equal to 3 times 108. Then if I keep going and simplifying this, I will get 3 times 6 times root 3, and I will get 18 root 3. So I've simplified 3 root 108 to 18 root 3. I'm going to erase the 8. It doesn't look like an 8. I'm going to rewrite it. 18 root 3. Okay, so that's good. I've done that. Now I'm going to go back and I'm going to try to simplify 2 root 98. So 2 root 98, I want to think about the factors of 98 and whether or not there are any that are perfect squares. And I remember that if I divide 98 by 2, I get 49 times 2, and that 49 is 7 squared, so 49 is a perfect square. So I'm going to write 2 root 98 as 2 times root 49 times root 2. And then if I go ahead and simplify that, I am going to get 2 times 7 times root 2. And if I simplify that more, I get 14 times root 2. Wait, sorry, I'm just going to say 14 root 2. There we go. Okay, so now I've simplified 2 of the 3 radicals that we have here in this expression. So I'm actually going to kind of put brackets around them so we know what is belonging to what, because it can get a little bit confusing. Alright, so now we're moving on to the last mixed radical, and it is 4 root 147. And again, I'm going to be considering the factors of 147 to see what I can multiply that is a perfect square that will give me 147. And again, I realize that 49 is a perfect square, and that 49 times 3 gives me 147. So I am going to use that to simplify this mixed radical. I'm going to write 4, should be the line above, sorry. I'm going to write 4 times root 49 times root 3. I don't know, wait, no, yes, sorry, I'm losing my train of thought, apologies. So then I'm going to go ahead and simplify that. I know that root 49 is 7, so I'm going to say 4 times 7 times root 3, and then I'm going to add that to the other mixed radicals I have, and I'm going to get 28 root 3. However, once we've gone ahead and we've gotten to this part, we see that we have 2 mixed radicals that are actually like radicals. We have 18 root 3 and 28 root 3 that both have the same radicand, which is 3. They have the same radicand value of 3, or they're both being multiplied by root 3. Either way, it means the same thing. So we can go ahead and simplify this further by adding 18 and 28, and then we will get 46 root 3 plus 14 root 2, and that is the complete simplification of this radical expression, and we are done with this example. Yay! Okay, let's do another example. Alright, let's erase this and do another example. Okay, example E. So example E, we are saying that we have 9 root 12 plus 5 root 48. And we want to simplify this like before. This is actually a little bit easier in my opinion than the last example, just because there are less mixed radicals that we have to deal with. So, but again, we're going to start with 1 and then work our way to the other side. So, other side, there's no other side, but like to the next, to the right, start at the left, work to the right. Anyway, so we're looking at 12 and we want to see what factors of 12 are perfect squares. we know that 4 times 3 is equal to 12, and that 4 is a perfect square because it is 2 squared. So we're going to use that. So root 4 times 9 times root 3 is this here, the simplification so far, 4, 9, root 12. And then we're going to do 9 times 2 times root 3, because we evaluated 4 root 4. And we're going to get 18 root 3 for this part. And we're going to put some brackets around so we don't get it confused with the next part that we do. And now we're going to move on to the next mixed radical that we want to simplify, which is 5 root 48. So we want to look at 48 and look at the factors of that and see what can we rewrite that as. So we have a perfect square, and we realize that 16 times 3 gives us 48. So I'm going to rewrite this mixed radical as 5 times root 16 times root 3. And then I'm going to go ahead and simplify that further by saying 5 times 4 times root 3. And then I'm going to go ahead and write that again as 20 root 3. And I'm going to put some brackets around that to kind of separate it out. And then we get down to this step again, and we realize that we have two like radicals. These two mixed radicals that we have now are actually like radicals. They have the same radicand again, so that means we can add them together to simplify this even further. So our final answer will be 18 root 3 plus 20 root 3. We're only going to be adding the coefficients in the front. The radicand will stay the same. So, well, the radical and like the radicand will stay the same. So we're going to have 18 plus 20, which is 38 root 3. And that is our final answer. And we are done this example. Okay, let's move on to another example. Just going to get rid of this. Don't mind me. All right, example F. It's our second last example, guys. We're almost there. And then we're going to be pros with radicals. Okay, so this one is quite a tricky example because we're bringing multiplying into the mix. So we have 3 root 2 minus 2 root 3. And we're going to be multiplying this by 4 root 3 minus 5 root 2. Okay, so what we want to do here is we still want to apply the principles of FOIL, because even though we are dealing with radicals, those rules still apply. If you remember from grade 10, FOIL, we are going to be doing first, outer, and then inner, and then last. So just kind of draw out what that looks. We're going like this, and then we're going to be going like that. In terms of multiplication, that's how we're going to be multiplying. Oh. So basically, if we multiply the first part, so we have 3 root 2 times 4 root 3, we are going to get, we're going to multiply the coefficients first, so 3 times 4 is 12, and then we're going to multiply the radicals, and like more specifically the values inside the radicand, we're going to be multiplying those, so we get root 6 because 2 times 3, so we're going to get 12 root 6 for the first part. Then we're going to be multiplying 3 root 2 times negative 5 root 2, so we're going to be getting negative 15 root 4. I know you might be like, oh, but root 4 is equal to 2. We're going to get to that in just a second. If you're thinking that, you're thinking ahead, good job. If not, don't worry. So, and then the next part we're going to be doing when we're multiplying is negative 2 root 3 by negative 2 root 3 times 4 root 3, which is going to give us negative 8 root 9. Again, don't worry, we're coming back to these perfect squares in just a second. And then if we multiply negative 2 root 3 with negative 5 root 2, we are going to get positive 10 root 6. Okay, so now that we've kind of multiplied everything out using the FOIL method, or distributive property, whatever you'd like to call it, we are going to simplify it best we can. because we have these perfect squares here that we want to kind of write out normally. So we're going to say negative 15 times 2 and negative 8 times 3, and then we're just going to carry the rest of it down. I don't know why I switched pen colors. I'm so sorry if that bothers you. Anyway, we're going to say 12 root 6 minus 30 minus 24, and then we're going to have plus 10 root 6. Well, if we look here, we can see that 12 root 6, I want to underline that in red. You can see that 12 root 6 and 10 root 6 are like radicals. This means that we can add them together. And then we can also deal with the negative 30 minus 24 because those are just integers and we can do normal subtraction there. So if we simplify the above statement, above the above expression, we get 22 root 6 minus 54. And that is our answer. And we have successfully simplified this. A little bit challenging because of the multiplication and the FOIL method that you have to use to distribute everything, but once you break it down step by step, it's not that bad. Okay, let's move on to our last example. Just gonna delete all this. All right, so for our last example, we have a rectangle. Please do not roast my drawing skills. I know I cannot draw. Okay, so this is a rectangle. See, right angles. Okay. And one side of the rectangle, oops, I don't know what I'm drawing here. One side of the rectangle has a side length of root 27 units long. And the other side length of the rectangle is 3 root 2 units long. So what I want to do is I want to calculate the length of the diagonal of the rectangle. Now, the way I'm going to do this is I'm going to use the Pythagorean Theorem, which, in case we forgot, is a squared plus b squared equals c squared. So what I want to do is I'm going to assign either side to a or b, it doesn't matter. So let's just say that this is a, this is b. You don't have to assign them, I'm doing that for the sake of this tutorial. So then I'm going to say that 3 root 2 squared plus root 27 squared is equal to c squared. So if we square 3 root 2, we get 9 times 2. And then because 3 squared is going to be 9, and then root 2 squared is just 2, and then root 27 squared is just 27. That's equal to c squared. So 9 times 2 is 18. 18 plus 27 is equal to c squared. So 18 plus 27 is 45. So 45 is equal to c squared. We want to simplify this though. So we're going to say c is equal to root 45. But we know now how to simplify a radical. So we're not just going to leave it like that. We're going to be like, if there's any multiples of 45 or any factors of 45 that are perfect squares, we are going to take them out and like evaluate them. So in that case, that would be root 9, because 9 is 3 squared. And then we have root 5. So it's going to be 3 root 5. And that is our value of c. c is equal to, therefore, c is equal to 3 root 5. I'm going to box it off in blue this time because I used red to solve the problem. But yeah, that concludes this video and tutorial on radicals. This is a bit of an introduction. Once you feel more comfortable with radicals, you can learn how to rationalize denominator numerator of fractions that involve radicals and whatnot. I actually have a video on that that's up. It's in my grade 12 calculus playlist if you want to check it out. If not, thank you so much for supporting my channel, and if you have any lingering questions about the topic of radicals, feel free to comment them below and I will try my best to get back to you. If not, I will see you in the next video. Thank you so much. Bye.